Honors Chemistry Final Review. You can access this video and this review at srhschem.wikispaces.com or on my YouTube channel, LaFell Labs. The first section is about acids and bases. In question 1, we need to compare the ionization of hydrobromic acid, which is a strong acid, to the ionization of acetic acid, which is a weak acid. How is a strong acid different from a weak acid? So the difference is that a strong acid ionizes 100%. What that means is that it completely breaks apart and forms ions. So every single strong acid molecule will break apart and form ions. A weak acid ionizes less than 100%, and usually it's a lot less than 100%. So in this case, that one didn't break apart, this one did ionize, and that one did not. So we only see about a third of them ionizing for a weak acid. Write an equation to show the ionization of HBr in water. So if I start with HBr, that's really made of a hydrogen ion and a bromide ion. If I add that to water, those two ions are going to break apart. So I end up with an H plus and a Br minus. It's important to note that because this is an acid, whenever that H plus is formed, it's actually going to piggyback onto a water molecule and form a hydronium ion. But if we want to write the ionization, that's our formula. We get H plus and Br minus. Now let's write an equation to show the ionization of acetic acid in water. So acetic acid, this molecule, is actually made of two ions, just like the HBr. So we have an H plus ion, and then we have this acetate ion. So this is a polyatomic ion made of many different atoms that have one overall charge. If I add this to water, just like the HBr, we're going to get an H plus that's going to piggyback onto a water molecule to make a hydronium, and we're going to get an acetate with a minus charge. So overall, our formula, we get hydrogen ion and acetate ion. Draw a picture showing the correct amount of ionization for 3 molecules of HBr. So HBr is a strong acid, which means that if I start with 3 HBr molecules, they're all going to break apart, and I'm going to get 3 H pluses and 3 Br minuses. So I see 100% ionization. In the case of acetic acid, to draw a picture showing the correct amount of ionization, this is a weak acid. So they're not all going to break apart. So just this one is going to break apart. So I get 2 acetic acid molecules, 1 acetate ion, and 1 hydrogen ion. In actuality, the ionization for acetic acid is really about 5%. So it would be kind of difficult to draw that because I'd need to draw about 20 and then show one of them broken apart. So really it's much, much less than 100% and actually much, much less than what we see on the screen. Next question, what is an Arrhenius acid? What is an Arrhenius base? And provide examples of each. So according to the Arrhenius definition, an acid is a compound that forms H plus ions when added to water. So something like HCl or citric acid, those are going to yield H plus ions, just like our 2 examples in the previous questions. Bases are compounds that form OH minus ions when added to aqueous solution. So sodium hydroxide is an example of a base. So that would yield an Na plus ion and an OH minus ion. Calcium hydroxide would give me 1 Ca plus 2 ion and 2 hydroxide ions with a -1 charge. Next question is about the Bronsted-Lowry definition of acid and bases. So considering both the forward and reverse reaction, which substances are acting as Bronsted-Lowry acids in the equation? So in order for NH3 to become NH4, it needs to gain a hydrogen ion. And if I wanted to remake water, NH4 would have to give up one of its hydrogens to make water. to the OH minus. So these are both hydrogen donors. So if we look at the forward reaction, water donates a hydrogen to NH3, and if we look at the reverse reaction, NH4 donates a hydrogen to OH minus. So because they are hydrogen donors, they're both acting as acids according to the Bronsted-Lowry definition. In Bronsted-Lowry, bases are going to be hydrogen acceptors. Use the equation below to explain why water is both an acid and a base. So this equation here is showing the self-ionization of water. So one water can donate a hydrogen ion to the other water. So this matches the Bronsted-Lowry definition. Water can both donate and accept hydrogen ions, so it is acting as both an acid and a base. The Arrhenius definition says that an acid is something that forms H plus ion when in solution. So remember, whenever we form H plus ion in water, we end up with hydronium. So that's what that H3O plus is. We also get OH minus, which makes water a base as well. Next question, put the pHs in order from most to least to most H plus ion. So the highest pH is the one that is the most basic. It is the least acidic. So it is H plus ion that dictates acidity. So the highest pH is going to have the least H plus. The lowest pH then is going to have the most acidic pH. So that one is going to have the most H plus ion concentration. Next question, a 15 milliliter sample of hydrochloric acid is neutralized by 6 milliliters of 0.25 molar sodium hydroxide. What is the molarity of the HCl? So this is ultimately just a stoichiometry problem. So let's look at the information that we have. Whenever we are neutralized, that means that the pH is at 7. And when the pH is 7, that means that H plus ion concentration is equal to OH minus ion concentration. So I'm going to use the info that I have about the acid and the base to figure out what the concentration of the acid is. So I know that I have 6 milliliters of 0.25 molar base, and I have 15 milliliters of an unknown molarity acid. So first thing I'm going to do here, I'm just going to do a stoichiometry problem. I'm going to use my 6 milliliter and my 0.25 molar to figure out how many moles of NaOH I used up. Then I can use a balanced equation to go from moles of NaOH to moles of HCl. And then if I divide by that 15 milliliters, that can get me to molarity. So first, I'm going to write the concentration in a couple different ways. 0.25 molar is the same thing as saying 0.25 moles in 1 liter, which is the same thing as saying 0.25 moles in 1,000 milliliters. And here's my balanced equation. So I have 1-to-1 stoichiometry for HCl and NaOH. So that makes my mole ratio very easy. So I'm going to start with my 6 milliliters of NaOH. And I know that there are 0.25 moles for every 1,000 milliliters of NaOH. And that's just what I wrote before, given the concentration of the NaOH. So at this point, if I solved, that would give me moles of NaOH. How many moles of NaOH reacted? I want to figure out the concentration of HCl. So I need to convert my moles of NaOH into moles of HCl. So this is my mole ratio, which comes from my 1-to-1 stoichiometry of my balanced equation. So at this point, if I stopped, my answer would be in moles of hydrochloric acid. I want molarity, so that's moles per liter. I know that my total volume of HCl was 15 milliliters. So if I stopped here, this would give me moles per milliliter. I want moles per liter. So if I multiply by 1,000, that's going to give me moles per 1 liter. So whenever I multiply across and solve everything, I get a concentration of 0.1 moles per liter. So I have 0.10 molarity hydrochloric acid. NaOH is a strong base. What is the pH of a 0.001 molar solution of NaOH? Compare the hydronium ion concentration and the hydroxide ion concentration. So first we need to know our equation. pH is the negative log base 10 of the H plus ion concentration. The problem is we don't have H plus ion concentration. We are given the concentration of the base, which means that we have the concentration of OH minus, so we can find the POH. So if I take the negative log of my concentration of my sodium hydroxide, I get a POH of 3. Then I need to know that the sum of my POH and my pH is 14, so that means that my pH has to be equal to 11. So because a pH of 11 is basic, that means that the hydronium ion concentration is less than the hydroxide ion concentration. So if we have a high pH, we see lots of OH minus and very little H plus. And if we have a low pH that's acidic, we would see lots of H plus and a little bit of OH minus. According to the Arrhenius definition, what is formed when an acid and a base react? So if I start with an acid, such as hydrochloric acid, and a base, like sodium hydroxide, I'm always going to form two things. So one of those things is going to be a salt. And the other thing that I'm going to form is going to be HOH. In other words, I'm going to make water. So if I start with acid and a base, I'm going to form a salt and water. Now that salt is not always going to be NaCl. It depends on what ions are involved. So, for example, if I were to react sulfuric acid with calcium hydroxide, the salt that I would form would be calcium sulfate and also water. The next section is about gases. So describe the motion of an ideal gas according to kinetic molecular theory. So according to kinetic molecular theory, gas particles are considered to be small hard spheres with insignificant volume. The gases are in rapid, constant, random motion. So in this simulation here, these represent different gas particles. Notice that they almost seem to move independently of each other unless they collide, in which case their paths will change. Notice that some of the particles are moving a little bit faster, so they don't all have the same kinetic energy, but they do have the same average kinetic energy. All collisions are elastic, meaning that no energy is lost. So if one slows down, the other absorbed that energy and sped up. So no energy is being lost between those collisions. Explain why it is so easy to compress a gas, but so difficult to compress a solid. So gas particles are very, very small compared to the volume that they take up. So there's lots of space between them. Liquid particles, however, have very strong intermolecular forces. They're very strongly attracted to each other, which means that they are very close together. So since there's so much space between gas particles, it's very easy to compress them together before they start touching each other. With liquid, they're already really close, and even more so with solid. Complete the table by filling in what would happen to the gas based on the indicated change. If the box is filled in, assume that that variable is constant. So for A, if the pressure decreases by half, the volume is going to go up by a factor of 2. So this is an inverse relationship. So that means that if one goes down, the other goes up. If pressure is decreased, it's because the gas has to take up a bigger space so that we get a lower pressure. And temperature would remain constant. For the next one, if the temperature is tripled and volume stays the same, that means pressure will also be tripled. So direct relationship here. For the last one, if the volume increases by 2 times, the temperature has to increase by a factor of 2 as well. This is to maintain the constant pressure. Normally, if you make a container bigger, that's going to cause the pressure to go down because there'll be fewer collisions. So that gas would have to heat up in order to maintain a constant pressure. A sample of hydrogen gas is collected over water at a temperature of 29 degrees Celsius. What two gases are present above the water? So I'm going to have a mixture of hydrogen gas and water vapor. So this picture shows how we would collect this hydrogen gas. So there's some kind of reaction that's producing hydrogen, and we can bubble that hydrogen through water and then catch it in a test tube. That does mean, however, that the hydrogen gas is going to be wet. In other words, it's going to be mixed with water vapor. If the total pressure is 300 millimeters of mercury, what is the pressure of the hydrogen gas alone? So we're going to need to use our vapor pressure of water table. So the total pressure is going to be the pressure of the hydrogen gas plus the pressure of the water vapor. My total pressure is 300 millimeters of mercury. We are at 29 degrees Celsius. So if we look at our vapor pressure of water, if the temperature is 29 degrees Celsius, the water is going to exert a pressure of 30 millimeters of mercury. So that means that in order to find the pressure of the hydrogen gas, I need to subtract. So of the 300 total, 30 are from water. So the other 270 millimeters of mercury are from just the hydrogen gas. Next question, consider the cylinders which have movable pistons. How many moles of gas are present in each cylinder? So both pistons have the same initial conditions. They're both at 2 atm, 6.5 liters, and 200 K. Therefore, as long as these are both ideal gases, they must have the same number of moles for each gas. What conditions would make the gas in cylinder A be more ideal? So in an ideal gas, those particles are going to be far apart and they're going to have no attractions. So anything that I can do to lessen those attractions will make a gas behave more ideally. So if I have the gas at a really high temperature, those particles have a lot of kinetic energy and they're moving so fast that there's no time for them to interact with each other. Those attractions become weak. Low pressure. So particles must be very far apart and rarely collide in order for the pressure to be low. So once again, this reduces the interactions between particles. If the conditions in cylinder A change to a pressure of 5 atm and a temperature of 300 K, what is the new volume of the gas? So here are my initial conditions, and here are my final conditions, and I'm solving for the final new volume. So this is a job for the combined gas law. Because I have all three variables, pressure, temperature, and volume, I need the combined gas law. So at this point, I just need to plug in. So I'm solving for V2, so I left that as V2. You can cross multiply and solve. So I end up with volume 2 being 3.9 liters. (14) is a table about the different gas laws. First gas law is Boyle. So Boyle, the equation is P1V1 equals P2V2. So you can remember Boyle is a VIP. So that means that volume and pressure have an inverse relationship. So if my volume is small, that means I have a very small container of gas. So those particles are going to be more likely to collide and we have high pressure. In our practice problem, we'd have to identify our conditions. And then we can just rearrange our equation. So I rearranged this to solve for P2, the new pressure of the gas. And plugged in all of my numbers. We see that liters cancels and I get 1.75 atm. Let's check to make sure that makes sense. My volume got smaller, so my pressure should get bigger. And it does. We get 1.75 instead of 1.5. Next is Charles's law. So Charles is the relationship between temperature and volume. So you can remember Charles watches direct TV. So that means the relationship between temperature and volume is direct. Pressure is constant. So if the container gets hotter, it also needs to get bigger in order for the pressure to stay the same. So let's identify our starting conditions. Because this is a proportion, it doesn't matter if I use Celsius or Kelvin. That would come into play if we were doing the ideal gas law and we were solving using an R constant that had units of Kelvin. So it's okay for us to keep this in Celsius. So I'm going to rearrange to solve for V2. So that means I got to multiply both sides by T2. Plug in and solve. Notice that degrees Celsius cancels. And we end up with volume 2 being 99 liters. So let's make sure this makes sense. The temperature went up, so the volume should go up. And it does. So this matches what we know about Charles's law. Next is Gay-Lussac's law. So Gay-Lussac is the relationship between temperature and pressure. And you can remember that Gay-Lussac directly touches people. So the relationship between temperature and pressure is direct. So in order for volume to stay the same, if my temperature goes down, my pressure needs to go down. So we can identify our conditions. We are solving for P2. So I rearranged by multiplying both sides by T2. Plug in my numbers. We see that the Celsius's cancel, and we get P2 is 2.5 atm. So let's make sure this matches. The temperature went up, which means that the pressure should go up. So it goes up from 0.5 to 2.5. Next questions are about the rate of reactions and kinetics. So how would the following influence rate of reaction? Explain how each of the following would influence the rate of reaction in a sealed container. So number of collisions. If there are more collisions, that's going to mean more reactions. So that will form more product, particles are reacting more, we increase the rate of reaction. Energy of collisions. So the more energy there is, that's going to supply the activation energy necessary for the reaction. So this can increase the rate of reaction. Collisions with the wall of the container isn't a reactant, so this is going to have no effect on the rate of reaction. Angles of impact. So if those angles are correct, a product will form and that will increase the rate of reaction. Use collision theory and surface area to explain why flour burns slowly in a pile but quickly when blown into the air. So burning is a chemical reaction with oxygen. When we blow flour into the air, that increases the surface area of the flour, so that allows many collisions between the flour and oxygen molecules. More collisions will make it easier and will increase the rate of the burning reaction. Complete the graph to show the relationship between rate of reaction and temperature. So a higher temperature is going to mean more collisions between reactants because the particles are moving faster. This is going to put us closer to the required amount of activation energy needed for the reaction to occur. So higher temperatures will usually speed up a rate of reaction. Design an experiment to determine the effect of surface area on the rate of reaction between magnesium and hydrochloric acid. So first, what is a possible claim about the effect of surface area on the rate of reaction? So a possible claim that we could make is that a higher surface area will lead to more collisions, which should increase the rate of reaction. So in order to test this claim, we need to see how long it takes for different surface area samples of magnesium to react with hydrochloric acid. So for a procedure, we can measure out 1 gram of each type of magnesium using a scale. So we can use magnesium ribbon and magnesium powder. The magnesium powder is cut up into much smaller, finer pieces, so that means it has a greater surface area than the magnesium ribbon, which is like a flat piece of magnesium. I want to make sure I have the same mass of each because I want to make sure that the only reason one reacts faster than the other is because of surface area, not because one of them had more magnesium. So I can put that magnesium into a beaker and measure out 10 milliliter of 1 molar hydrochloric acid using a graduated cylinder. Again, I want to make sure I have the same amount of acid in each, so I know the only reason one reacts faster than the other is because of the surface area. I need to pour the hydrochloric acid into one of the beakers with the magnesium and time the reaction until it is complete and there's no magnesium left using a stopwatch. Then record this information. Next, I'll need to repeat those 2 steps for the other type of magnesium. So the independent variable is what changes from trial to trial. So that's going to be the surface area of the magnesium. The dependent variable is what's being observed or measured. In this case, we're measuring the rate of reaction by recording reaction time. Constants are going to be things that have to stay the same for all trials. So I want to make sure that the only reason the dependent variable, the reaction rate, changed is because of the independent variable, because of the surface area. So everything else needs to be kept constant. So the mass of the samples, the timer used, the scale used, the temperature that this reaction is done at, the brand, the age of the magnesium, I want to make sure that everything is the same so that the only reason reaction time changes is because of surface area. So a sample data table needs to include the independent variable, which is the surface area, the type of magnesium, the dependent variable, which is the reaction time, and observations. The next section is about thermodynamics. For each of the following, determine if the reaction is endothermic or exothermic. So first I have solid water becoming liquid water. This is also known as melting, so heat has to be absorbed to melt something, making this endothermic. Because it is endothermic, delta H will have a positive sign. For the other one, I have a gas becoming a liquid, so I'm condensing. In order to condense, I got to lose energy. Energy has to be released, making this exothermic, and delta H has a negative sign. A substance was heated and the temperature was recorded every minute. So using the data, sketch a heating curve diagram. So if we look at our data, we have 2 places where it goes flat. Those are going to be phase changes that are occurring, and then temperature increasing in 3 places. What is the boiling point and the melting point of the substance? So first melting would occur. This is a heating curve. So the first plateau is melting, which is at 18 degrees Celsius. And the second plateau would be whenever we have boiling happening. So that would be at 30 degrees Celsius. Which phase has the most kinetic energy and which has the least? So kinetic energy is the energy of motion. So the one with the most motion is going to be the gas, and the one with the least amount of motion is going to be a solid. During a phase change, what is the energy being used to do? Why does it remain constant? So during a phase change, that energy is being used to cause the phase change, and it does that by weakening the attractions between particles. So at this point, the kinetic energy remains constant because temperature is constant, and the potential energy is increasing. Show the direction of heat transfer for the picture below. What happens to the temperature of each block? So heat will flow from hot to cold, and the heat is never going to stop flowing, but once the 2 blocks are at the same temperature, the amount of heat flow is the same in each direction. So heat will flow from A to B, and that's because A is hotter. This will stop, or rather it will, the temperature will stop changing once they're both at the same temperature. So the temperature of block A will go down and the temperature of block B will go up. Next question, bromine atom reacts with bromine atom to make a bromine molecule. So a bond is being formed because 2 atoms are combining to form a molecule. And energy is a product, which means energy is being released during this reaction. Bond formation is also exothermic. So bond breaking is endothermic. I don't have any bonds to break because I have 2 atoms here. There's no bonds between them. I'm only forming a bond between 2 atoms. So this is exothermic. Entropy is the number of specific ways a system can be arranged. So which of these is going to have the greatest increase in entropy? So if I go from a solid to a liquid, this is going to be an increase. So we go from low energy solid to high entropy gas or liquid. A gas to liquid is going in the opposite direction, so that's a decrease in entropy. Solid to gas would be an increase, and liquid to solid would be a decrease. So between the two that are increasing, which one is a bigger increase? So if I go from a solid to a gas versus going from a solid to a liquid, we see that solid to gas is a bigger entropy change. Next, label the enthalpy diagrams. So we'll start with the first one. Label if it is endothermic or exothermic. So this reaction is going to be exothermic because the products are lower than the reactants. So that means that I had to release energy in order for this to happen. Delta H is going to be the difference between reactants and products, and that value is going to be negative. Activation energy is the energy that I need to break apart my reactant bonds. So it's the endothermic part of the reaction. So activation energy needs to be absorbed. It's always endothermic. And in this case, it's the reactants to the top of the hill. If I were to add a catalyst, that would just make that hill smaller, which means that my activation energy would then be smaller. On the other graph, this is going to be endothermic, and I know that because my products, in order to form, they're higher energy, so they have to absorb heat. Delta H is once again the difference between reactants and products, except in this case, it's going to be positive. Activation energy, once again, is reactants to the top of the hill. It's the part of the reaction where I have to absorb energy in order to break reactant bonds. In this case, my hill is a little bit bigger, so my activation energy is bigger. But the catalyst would still have the same effect. It just makes that activation energy a little bit smaller. This will increase the rate of this reaction. How much heat is needed to melt 15 grams of ice? And the heat of fusion of ice is 334 joules per gram. So that means that if I have 1 gram of ice, I need 334 joules to melt it. So I'm going to start with 15 grams of ice. 1 gram of ice requires 334 joules, which means to melt all 15 grams, I need 5,010 joules. The next section is about solutions. So the first one is to draw the interaction between water and dissolved NaCl. So Na is a cation, which means that the negatively charged oxygens are going to face the positively charged sodium ions. For chloride, we see the opposite. The positively charged hydrogen is going to face the negatively charged chloride ions. So this is just based on charges. Water is a polar molecule. The hydrogen end has a slightly positive charge, and the oxygen end has a slightly negative charge. Explain why NaCl is an electrolyte, but C6H12O6 is not. So that's glucose. So in order to be an electrolyte, 2 conditions must be met. There has to be ions in solution, and those ions have to be able to move. So if you look at salt, that's going to form Na plus ions and Cl minus ions. Sugar molecules don't break apart. They don't ionize. Therefore, there's no ions, there's no conductivity. It's not an electrolyte. Next question involves using solubility curves to answer some questions. Which chemical solubility decreases the fastest as the temperature increases? So we're looking at 20 to 40, so I highlighted that part of the graph, and I'm looking for ones where solubility is decreasing. So those are going to be ones that have negative slopes. The one that has the steepest slope is the one that is changing the fastest, so it's decreasing the fastest. Just note that all of the gases are showing decreasing solubility in water as temperature increases. A solution of potassium nitrate is prepared at 60 degrees Celsius and allowed to cool to 50 degrees Celsius. How much solid will precipitate out of solution? So at 60 degrees, I see that I can hold 105 grams. And at 50 degrees, I can see that I can only hold about 82 grams. So the difference is going to be how much precipitates out. So I can hold more at 60 than I can at 50. So the solution can't hold all of those 105, it can only hold 82. So it's got to drop, it's got to precipitate out 23 grams. What is a supersaturated solution? So a supersaturated solution is one whose concentration exceeds the predicted solubility at a given value of temperature and pressure. So an unsaturated solution, if I were to add more solute, it would continue to dissolve. Once I get to saturated, that means I'm holding as much of the solute as the solution can. And a supersaturated solution is one that's unstable. So this would actually cause crystals of the solute to grow. How many moles of NaOH are needed to prepare 2 liters of a 3 molar solution? So molarity is moles over liter, and I want a 3 molar solution. So if I were going to make 1 liter, I would need 3 moles of NaOH. In this case, I want to make 2 liters. I know that a 3 molar solution, 1 liter has 3 moles, which means I need a total of 6 moles of NaOH. So I would need to convert that into grams, and then I could weigh out that amount of NaOH using a scale, add it to my 2 liters of water, and I would get 2 liters of 3 molar NaOH. Complete the graph to show the relationship between temperature and solubility in a liquid for a typical solid. So for solids, heating is going to allow more of the solid solute to be dissolved, increasing the solubility. So think of whenever you try to dissolve sugar into tea. It's going to dissolve a lot better in warm tea than in cold tea. For gases, however, we see the opposite relationship. So for gases, heating causes the gas solutes to escape, decreasing the solubility of the gas. The next section is stoichiometry. Lithium reacts with aluminum chloride per the unbalanced equation below. So in order to do any stoichiometry, I need to have a balanced chemical equation. So we can use the inventory method to do this. I have lithium, aluminum, and chlorine on both sides of my equation. And if I count, I see that I have 3 chlorines on my reactant side and only 1 on my product side. So if I put a 3 in front of lithium chloride, that's going to fix my chloride, but now I've got 3 lithium and it's unbalanced again. So if I put a 3 in front of lithium, that will balance out my equation. So now that I have my balanced equation, I can do stoichiometry. How many moles of lithium are needed to react with 5 moles of aluminum chloride? So an important thing to note is that in front of the aluminum chloride and the aluminum, there's no numbers there, or we can write a 1. They both mean the same thing. So if I start with 5 moles of aluminum chloride, I need to convert that into moles of lithium. So that's a mole ratio. There are 3 moles of lithium for 1 mole of aluminum chloride. So that means that I would need 15 moles of lithium to react up all 5 moles of aluminum chloride. Next, what mass of aluminum chloride is needed to prepare 10 grams of aluminum? So I'm starting with my 10 grams of aluminum, and I need to convert that into moles of aluminum. So in stoichiometry, we're always comparing moles. So I want to go from grams to moles using the molar mass of aluminum. Next, I need to go from moles of aluminum to moles of aluminum chloride, and that's a 1-to-1 mole ratio. And since I want the mass of aluminum chloride, I need to use the molar mass to convert to grams. So I get 49.42 grams of aluminum chloride. The next question, how many grams of lithium chloride can be produced from 2 moles of aluminum chloride? So since I'm already in moles, I don't need to do any conversions, but I do need to convert aluminum chloride into lithium chloride, and the ratio is 3-to-1. 1 mole of lithium chloride has a mass of 42 grams, which means the total mass that I need is 254.364 grams of lithium chloride. What is the mole ratio of aluminum to lithium chloride? So we have a 3-to-1 ratio. And aluminum chloride to lithium chloride is a 1-to-3 ratio. Next set of questions are equilibrium. So here's my equilibrium reaction, and explain what would happen to the amount of A if heat were added. So if I increase the amount of heat, this is going to cause a shift towards the reactant. So whenever I add something, I have to shift away. So that will cause more A to be present once equilibrium is reestablished. What would happen to the amount of A if C were removed? So if I remove C, that's going to cause a shift towards products to replace the missing C that I took out. So that's going to speed up the rate of my forward reaction, using up my amount of A, so there will be less of it present when the system reestablishes equilibrium. What would happen to the amount of A if the pressure were increased? So pressure only affects gases, and all of my reactants are gases. So on my reactant side, I have 3 moles, and on my product side, I have 2 moles. So if I increase the pressure, equilibrium is going to shift towards the products, which is the side with fewer moles of gas. So we need to relieve the added pressure. So since I'm shifting towards products, I'm speeding up my forward reaction, and there will be less A present whenever we reestablish equilibrium. Compare the rate of forward and reverse reactions at equilibrium. So by definition, the rates of the forward and reverse reaction are going to be the same once we reach equilibrium. So we interpret that as no change in the system. The forward and reverse reaction are still happening, it's just that they're happening at the same rate, so there's no observable change. Now that does not mean that the amount of everything is equal. So if we look at our example equation here, I have much more hydrogen than I have ammonia and nitrogen. So they're not necessarily going to be the same number each, but they will stop changing because the rates are the same. What could I do to increase the production of D? So this is a very common problem in chemistry. How can I change my reaction conditions to produce more product? So anything that pushes equilibrium towards product. So I could remove heat, I could remove C or D as they form. I could add more A and B. I could increase the pressure, so I would shift to the side with less moles. Next section is about nuclear chemistry. So which of the following is fusion? So the first one is beta emission. I start with a hydrogen and I make a helium and a beta particle. So that's not fusion. The next one is fission because I start with a big heavy uranium atom which splits apart into lighter atoms. Next one is fusion, and that's because 2 light nuclei, 2 hydrogen, are fusing together to make a heavier nuclei, which is helium. The last one is also fission. Uranium is being split apart into smaller nuclei. The half-life of a radioactive element is 6 days. How much time would be needed for a 60-gram sample to decay until only 7.5 grams remain? So if I start with 60 grams, one half-life would be 30 grams, another half-life is 15, another half-life is 7.5. So this took a total of 3 half-lives. 3 half-lives, each half-life is 6 days, so this is a total of 18 days. How much of a 100-gram sample of the element is left after 36 days? So 36 days is going to be 6 half-lives. So I'm going to take 100 and half it 6 times. So once I'm all said and done, I have 1.56 grams left over. I took half of 100 6 times. Explain how a nuclear power plant works to generate electricity, and what is a major disadvantage of nuclear power. So in a nuclear power, heat energy is created through fission, and that heat energy is transformed into kinetic energy by making liquid water into steam. So there's an increase in kinetic energy to go from a liquid to a gas. This steam is used to power a generator. Energy is then transformed into electrical energy using the generator. A major disadvantage is that the products of this reaction includes radioactive materials, and these require safe, careful storage for thousands of years in order to avoid any radioactivity being leaked into the environment. Some study tips: make sure you know when your exam is, get a good night's sleep, and you can make a study schedule. You should focus on areas of the review that you did poorly on or that you really didn't understand. And you can use srhschem.wikispaces.com for review.